We have talked about central tendency and dispersion already. The next topic is correlation. Now, of course, there is no concept of correlation in univariate setup. We need at least two variables to define correlation. When we first hear about correlation, it is in this bivariate setup, which is the simplest possible setup where correlation makes sense. There, the definition was like this. Correlation of x and y is equal to covariance of xy divided by the product of standard deviation of x and standard deviation of y. But once we increase the data dimension, that is number of variables, above 2, new possibilities start cropping up. That's what we plan to discuss now. When we say that x and y are correlated, we mean that there is a linear relation between their values. Like one increases when the other increases. Or maybe it's just the opposite, in which case one increases when the other decreases. Now such a relation need not be exact as I have shown. It rarely is in practice, so there is some amount of noise. Correlation measures both the direction, positive or negative, as well as the strength of such a relation between two variables. A perfect linear increasing relation means that the correlation is equal to 1. And similarly, a perfect linear decreasing relation will lead to the value -1. All other cases produce intermediate values. Now this much you already know. Now when we have a third variable z, we might ask the question, are x and y correlated only through z? Let's understand what this question really means. We shall do so using an example. Telescopes, as mentioned in textbooks, have eyepieces. That's a lens that we look through. Now, modern astronomical telescopes, however, do not have eyepieces. Instead, they are fitted with a CCT array, a grid of photosensitive elements which records the image and passes it to a computer. The situation is very much like that of a mobile camera. Now, it is seen that the noise level in the final image is positively correlated with the ambient temperature. The warmer the surroundings, the noisier the image. Scientists suspect that the main culprit is the CCT plate. Warmer environment causes the CCT plate to get warmer too, and that causes the increased level of noise. Thus, the suspicion is that the outside temperature affects the image quality only through the CCT temperature. If we can somehow manage to keep the CCT temperature constant, the image quality will not deteriorate even if the outside is hot. This is just a suspicion. How to check this? One simple way is to carry out an experiment like this. Keep the CCT temperature fixed by means of some external cooling device and change the outside temperature. If the image quality remains unaltered, then our suspicion is corroborated. If, however, the image quality is still affected by the outside temperature, then surely there is some path other than through the CCT by which the temperature effect is still sneaking through. Now this idea is present whenever we have 3 or more variables. Here x and y are correlated. Now z is a third variable. The question is, are x and y related directly or through z only? In other words, we are asking whether this direct arrow really exists or the relation comes only through z. This is what we plan to explore statistically in the next video.